Now, coming to the last video on stochastic calculus, uh, of course, that's not to say that we have come to the end of stochastic processes. I think I still have a few topics, I think a few more advanced topics like Monte Carlo simulation, things like that, to round off the stochastic processes playlist. In this video, we'll look at stochastic calculus applications in finance. That's one very key area where stochastic calculus is applied. Okay, so stochastic calculus applications in finance. First off, why stochastic calculus in finance? Why is it necessary to have stochastic calculus in finance? Financial markets are uncertain and evolve randomly due to news, economic events, investor behavior, and we model this using stochastic processes such as Brownian motion and stochastic differential equations. Of course, most of the times when a new president is elected, that has some impact on the market one way or the other. Like probably based on the kind of policy the president has or something, it might sway the market in one way or the other. So, I mean, so there's a lot of volatility in financial markets. So, with again remind ourselves of the Brownian motion, which is like the most important stochastic process, as we can, I mean, we have been seeing. So, Brownian motion also known as the winner process. So, we see that a process W sub t is a standard Brownian motion if it obeys these four conditions. First of all, W0 is equal to zero. That means that at the beginning of time, at time zero, the process is zero. Then it adds independent increments, and then Wt minus Ws is normally distributed with mean zero and variance T minus S. So the variance is basically dependent on the time. So then you also have continuous parts, and the fact that the process is nowhere differentiable. So dw dt is not it doesn't exist, right? Because of the stochasticity of the process. Then we have properties like the expectation of any Brownian motion, any stochastic process is zero, and the variance omega sub t is t, like this. Um, yeah, of a Brownian motion at least, the expectation is zero. Let me not see any stochastic process so I don't overgeneralize. Then of course we've simulated Brownian motion a whole lot, and we have something like this. And if you remember, this is how, if you're used to financial market, this is how stock prices also move, right? Or you trade in forex and things like that. This is how you have the curves moving over time because of the high stochasticity and randomness that you have in the system. Okay. Now we move on to stochastic differential equations, which we considered in an earlier video. So the general form of the stochastic differential equation is given as dx of t equals mu, which is a function of x of t and time, dt plus sigma, which is also a function of x of t comma t, dwt, where mu is drift and sigma is the volatility. And then we have geometric Brownian motion, GBM. So here you have stock prices modeled as ds sub t equals mu s sub t dt plus sigma s sub t wt. The last video was dedicated totally to geometric Brownian motion because of its sheer importance. And then we also have the solution to this problem to be s of t equals s naught exponent mu minus half sigma squared t sigma omega w sub t, like that. Then we can then have, of course, we also experienced simulating a GBM, uh, a geometric Brownian motion system, like that. So, and then of course we even did multiple parts. So for Ito's lemma, which we have seen amply, so if x sub t follows dx sub t equals mu dt plus sigma d w sub t, then for a function f of x comma t, then df is df dt plus mu df dx plus half sigma squared d squared f dx squared dt here, then plus sigma df dx dw sub t. So we have an example of that in log of stock price. So imagine, let f of s, the function of stock price, be log s. Then we say that d ln s of t is equal to mu minus 1 over 2 sigma squared dt plus sigma dw sub t. Of course, that makes sense because if you look at the solution, it contains exponents. So if you take the log, right, it automatically expels this log side. So you have ln s naught and then multiply by the rest of the things, right? So that's what exactly is happening there. So this shows log returns are normally distributed. And then we have risk neutral measure. So under risk neutral measure, the S sub t is equal to R S sub t dt plus sigma S sub t d sub dwt raised power q. Where here, mu, we replace mu with risk, which is, and that with R rather, which is called the risk-free rate. Mu normally is actually the growth rate, right? So, but the risk-free rate now is what ensures there's no risk at all, right? Yeah. So because normally mu can be positive or negative. So if it is positive, it's the price grows. If it's negative, it's the price decreases. Then we have Black-Scholes equation. I mean, this is a very common thing that is talked about in financial circles. So for Black-Scholes equation, right, you have dv dt plus half sigma squared s squared d squared v ds squared plus rs dv ds minus rv equals 0. So here you have the variables f v now, which is the function of both s and t, is the price of the derivative or the option value. Then you have s, which is the price of the underlying asset. T is time, then sigma is volatility. We know that much up before now. Volatility of the underlying assets, and we have R, which is the risk-free interest rate. That's how the Black-Scholes equation goes. And then the meaning of each term is this. dv dt now talks about change in option value over time. That talks about time decay. And half sigma squared s squared d squared v. I mean, this whole term now simply talks about effect of volatility or uncertainty over time. Then you have rs dv ds, this third term, that is sensitivity to asset price growth, and then minus RV now, that is discounting at the risk-free rate. RV, that's discounting. And then that takes us also to Black-Scholes formula for European call option. So, I mean, this whole if you're into the business of option pricing and all of this, this will make a lot of sense to you. So like I think quants will be able to relate with this better. So C is S naught N D1 minus K e raised by minus RT N D2, where D1 is this expression and D2 is all this. And we have the variables. Now C is the price of the call option. S naught is the current price of the underlying asset. K is strike price. T is time to maturity in years, and R is risk-free interest rate, right? Then you have sigma, which is volatility of the underlying asset, and n naught, that's the cumulative distribution function of the standard normal distribution. So when you see this, all this ND1, ND2, that's the cumulative distribution function of the standard normal distribution. The interpretation of all of that is this, that when you have S naught N of D1, so that is the expected value of receiving the asset adjusted for probability, and K e raised by minus RT ND2 is the present value of the strike price weighted by probability. Then you have D1 and D2, which measure how far the asset price is from the strike, adjusted for time and volatility. Now, this formula gives the fair price of an European call option under the assumption of no arbitrage and log normal stock price behavior. That might sound like a lot of jargon to people who are not into the business of financial markets and all and things like that, right? So to simulate the Black-Scholes code, right? You just so we use SciPy now because we need num from there. We need num for the cumulative distribution function. So then we define Black-Scholes codes that takes values S, K, T, R, and sigma as seen in that formula, and then we have D1. We have D1 to be log S over K, blah blah blah. We have that expression based on the formula we have here, ln S naught over K. That's all of that here. D2 is also this. Then we have the return. It returns S star, you know, it returns this S here, which has been codified into D1 and D2. So we just call the D1 and D2 here. And then if we fix S to be 100, K to be 100, T to be 1, that's time, maybe 1 year, R is 0.05 and sigma is 0.2. Then we have 10. So that way that returns the value of C, which is the price of the call option. So we have that to be 10, maybe $10 or whatever units you want to be interested in. Then we have Greeks now. So for delta, delta is sensitivity to changes in the underlying asset price. Gamma is sensitivity of delta to changes in the asset price or curvature. Then vega is sensitivity to changes in volatility. Theta is sensitivity to passage of time, that's time decay. And rho is sensitivity to change in interest rates. Then we have the delta or call option. So delta is N of D1. And you have the variables delta, that's rate of change of option price with respect to asset price. All right, that is like the delta we have here. Then N of D1 is cumulative standard normal distribution evaluated at D1. So the interpretation for all this, delta measures how much the option price changes for a small change in the underlying asset price. For example, if delta is 0.6, it means that a one increase in the asset price increases the option price by approximately 0.6. Delta also represents the approximate probability that the option finishes in the money. Okay, so and we have a code for delta like that. You want to see the call option delta. So you define all the necessary formulas and state the parameters. Current stock price to be 100, strike price is 100, T equals 1, that's time to maturity in years, R is 0.05, that's the risk-free rate. And then we have sigma, which is 0.2, the volatility. And you have all of that, and you get 0.6368. So that takes us to the idea of Monte Carlo pricing. So that's C equals E raised per minus RT, expected value of maximum of ST minus K, comma 0. So so you have all of that, and that is 10.52 like this for Monte Carlo pricing. So we have some other advanced models, right? We have the Heston model, which is given as the S of t equals mu S of t dt plus square root of VT ST dW sub t. Then we have dVt equals k into theta minus Vt dt plus psi square root of Vt dzt. Then you have the jump diffusion, that's the S equals mu S sub t dt plus sigma S sub t dW sub t plus J sub t dnt. So these are some more advanced models you can look at apart from Scholes and all of that. So we come to practice problems here, having seen the applications of stochastic calculus in finance. So you want to try your hands on these questions 1 to 10 and questions 11 to 20. But of course, I have answers for you for two of them. For four, for instance, we verify numerically. What's question 4 again? Question 4 says verify numerically that the variance of W sub t is equal to t, right? I think that's where we do Brownian motion to see for several steps, and we see if the theoretical variance is equal to the empirical variance. So the method is simulate many Brownian motion paths at a fixed time to compute the sample variance, compare with theoretical value. So here now we take t to be 1, n is 1000 steps, dt is t over n, that's number of steps over time, then n sim, that's 10,000. So simulate Brownian motion paths. So you simulate it in 10,000 steps and all that. And of course, before now, 0.9 for empirical, theoretical is 1.0, that's perfect. So, and of course, if you keep running, the values always hover around themselves. So 1 point, so around roughly 1.0, to one decimal place. So the explanation there is that since W sub t is normally distributed with mean 0 and variance t, its variance should be t. So the simulation confirms that the empirical variance is close to the theoretical value, validating the property. Then you have the solution to 12 now. So for question 12 now, coding is what helps here. So compute the price of a European puts option using put call parity. P equals C minus S naught plus KE raised per minus RT. So in this case now, you have all this. So we compute the price of a European put option using put call parity. That's P equals C minus S naught plus K raised by minus RT. So, we define Scholes call S with parameters SKTR sigma. So we define D1 like before and D2 also, and then we return the value we need. Then we define the parameters as necessary. And then we have the call price 10.45 and we have the put price, that's the parity, that's 5.5. And the explanation is that put call parity ensures no arbitrage. So P plus S naught is C plus K e raised by minus RT. Then rearranging gives P equals C minus S naught plus K e raised by minus RT. This allows us to compute the put price directly from the call price without rederiving the full formula. So don't forget to try your hands on the practice problems, 20 of them. You have this, you have 10, the first 10 here, and then you have the second 10. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Yeah, we are gradually coming to the end of the stochastic processes playlist. I should have like four or more videos to make to complete this process. Some more advanced topics like Monte Carlo simulation and all of that. All right. So if you have subscribed to this channel, I thank you very much for doing that. If you have not, I mean, there's a lot to learn here. Why not subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like being the first to see some videos or seeing some videos exclusively as a member of the channel. You could also request for PDF copies of some of the notes I use for teaching some of those topics. You can also hang out with me online or physically if we're in the same geographical location at any point to discuss whatever interests you on this channel, be it mathematics, data analysis, data science, machine learning, scholarships, whatever, Python programming, all of that. We can talk about them. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.